this talk is gonna be about an idea I came up with, or I didn't come up with, but just I wanted to push to its logical extremes, and I found a lot of really surprising things, and I think a code quality metric that maybe we should be using a lot more. And it ends in it ends in some connections to other metrics or qualitative assumptions around like object-oriented programming or whatever. So let's do a brief recap. It's like, why do you want to keep your type small in the first place? What does the size of a type actually mean? So we can borrow the idea from set theory and just say that the size of a type is how many values it can hold, right? Types, what they have is terms, not necessarily values. And usually we talk about terms inhabiting a type. So one inhabits the type integer and so forth. And if you get a relatively quick intuition around it, we're just going to say, like, hand wavily, it's like, okay, if there's less things in these bags, then there's going to be a lot less unexpected things, right? Because if there's only one, if you know beforehand there can be only one thing in a bag in your code base, then you're not going to be surprised it's not the one thing you expect, right? If you have a proof of that. So a quick example is enums instead of ints, right? If you were writing code and you've decided that there's only going to be 3 marker colors for some highlighting app or whatever it is that you're writing, you won't have to worry about like, oh, what happens if for whatever reason I have an input that says 0 or -1. It's like, what color am I going to supposed to use? You get the compiler to check that it's one of these 3, otherwise it just won't compile. And you could go on and think about how this connects to ideas like entropy and state space and things. And there's a lot of interesting academic stuff that we're gonna just breeze over, because I think we should be more engineers and see what it can help us do as engineers. So again, a little bit of a recap on how you can count what's inside types, just to keep everybody on the level, like on the same level of understanding, not miss anybody. Basically, let's say that the type nothing in Scala, it has 0 terms. There's nothing inside nothing. The type unit just has the double parentheses, and it's called unit. You can see it's called unit because it just has one thing. Bools just have true and false. Byte has 256 elements, and so on and so forth, right? A string has an infinite amount, and so does list, right? And but that's not all you can do. You've heard of ADTs, so you can see that types can also be combined, right? You build out case classes, you build out new types, and they're called trees. And generally, we can notice that when you do these, when you do a case class, the cardinality of it, right? How many terms you can inhabit the new case class you wrote is actually a multiplication of the terms that inhabit each one of its components. And that's why it's called that's why this general idea is called algebraic data types, because they follow in terms of their cardinality, they follow the algebraic rules that you are used to seeing. So enums and either they add the cardinality. So if you have this enum here, the cardinality is 3, because for 1, there's only one value. You either have 1 or you don't. For 2, it holds a Boolean, so there's only a 2 of true and a true of false. So for 3, you have either the 1 or the 2 true or the 2 3, those 3. And then this one multiplies, it's 4. And maps are a data type that express powers. and and then you can see how it relates to functions. Functions are a map extends in Scala. It extends as a quirky remark. It extends partial function, and the connection is here. They are powers. There's more algebra you can do with types, derivation, etc., etc., etc. But we're not going to cover that right now. Let's just keep to these three and the nice things we can find. That's the recap. Does anybody have any questions so far?
Yes, Rodolfo, we have exact one question from Adam. Where does Philips use Scala?
In my department, basically, and a couple of other places, and the Software Center of Excellence inside it. So it's not the most common language inside Philips, but maybe that's going to change. So why maps are exponentials? So what happens when you have a map that goes from this data type, of 3, and then it maps out to a bool, right? What's the full, how much can you fill that map, right? How many ways can you fill that map? And it just so happens the number of ways you can fill that map is exactly 2 to the power of 3. And that's why they're exponentials. Same for functions, right? If you have a function that goes from a Boolean value to, let's say, unit, right? That's an interesting, right? Let's do Boolean to unit. That means the base is the unit, so it has only 1, and then the exponent is Boolean. And if you don't allow for side effects, then you need a function that returns a unit, and there's only one thing it can return. So the only function that lives there is just ignore the input, underscore, and fat arrow unit, right? If it's false, you're going to return unit. If it's true, you're going to return unit. And that means it's 1 to the power of 2. In fact, any function that returns unit is exactly, they're all the same. You could write that generically only once, because all you can do is return unit. There's more, but did that answer your question? Awesome. And thanks for everybody who added actual text in the chat. So I wrote a blog post that sort of does this for a particular use case, and the end result is that when you apply a couple of these rules, you can literally shrink, or I managed to shrink, the cardinality of the whole program from 10 to the 16, right? God knows how big that number is, to just actually 283. There are only 283 possible programs you could write to validate this this field. Good point. So Adam, you asked about your types being parametric. That's actually the next thing I'm gonna go over. So you got a little bit ahead of me. I will. I'll get to that one. So there's a couple of other talks, even in this one, that they go on and say, like, avoid primitive obsession, right? Usually the primitives, they hold too many values. Long is huge, or int, or even byte. Some just use as small a type as you need, right? So prefer the smallest possible type that lets you express the problem you're trying to solve. And a common thing, especially in people who come from languages like Java or C++ is that they will always use classes even when they should be using enums. In fact, even Scala in version 2 had horrible support for some types for enums. That's better now in Scala 3, but it's always better when you have to add instead of when you have to multiply. So prefer enums over products as often as it makes sense. So there's additionally your ability to use like a type refinement, and that is really useful to shrink the possible numbers, because, for example, how many ways are there to have a shuffled deck? I don't remember. It's combinatorical explosion, right, of however many cards are in the deck. But there's only one sorted deck. So if you know beforehand that the input you get is a sorted deck, then that's just one value that can come in. There's no surprises around what that function is going to do, either at the end, because you know it's going to be, it just has, you could replace the function with just a constant, right? And then this one is tricky, and it literally happened in a recommendation from the previous talk about avoiding list. He mentioned at the end, don't use sec. Try to say the parameter you want specifically. And it is because when you have a sum as a parameter, you can't use the distributive law of exponents. And I put this example in the code here, where the idea to calculate the area of a shape, right? And then shape is a sum, and you have however many shapes in your library, right? The square or rectangle, it doesn't matter. The function to calculate area, you're better off writing two separate functions, one for square and one for rectangle, than writing a function that pattern matches on the shape and then gets the area. Because if you're going to believe the whole premise that having a low cardinality in your code base is a worthwhile endeavor, you're better off having these two separate methods than one method that does both. And that'll actually, and now we're getting to where it connects to other things. This would defend what OOP people say about inheritance, that just define a common parent and overload the method in its children. You're effectively only using the smaller version, right? The version that has the cardinality I put below, instead of the one where you have 2 to the 30, 2 to the 64 plus the other one, which is huge. There's a better encoding than inheritance. You could just use type classes instead, but you now see a reason, a number that defends doing these things, right? Now you see, because you want to shrink the cardinality of your code base, you're not going to have this method. You're going to follow the single responsibility principle and actually segregate what it takes to calculate the area from a square from what it takes to calculate the area of the rectangle. And who was it that asked about Phillips? You can tell that I'm talking to a non-functional crowd about the benefits of a, let's say, functional approach to things. And that was really nice, right? That's a very good point, a very good rule of thumb to do. So don't put sums in the parameter position. right? That might go against some things. It's a Liskov substitution principle. I don't know. Maybe I'm wrong. Maybe it aligns with it as well. But that's a good guideline to really keep your cardinality small. So, Isaias, are there any tools to show the cardinality? I want to write one. I started an open source project to start writing those. So right now I'm only calculating tuples, but I really do want to write one. There's a lot of like interesting, super nice surprises and interesting stuff. I really want to explore this. Another thing. So you said, Adam, you said that you only had generics in your code base. What happens when you do that? You actually really shrink the cardinality of your code base. The moment that you turn a parameter into a type parameter, you can't know like in the body of the function, you can't know how many terms it has because it's just an A. Yeah. Sorry, reading the chat. You only know it's an A, so it literally shrinks it down and puts the cardinality to 1. If you want to still find other things about it, you can use then context bounds, which you could think of as type classes or whatever other encoding you want. And now you have in the body of the method, you only have the features that are available in some predicate. So if you do the calculation, whatever some predicate has will be less than you're assuming that my predicate functor is some. For example, let's say you want something Katz effect and you want something that has sync IO. You're better off putting sync IO as your requirement, because the cardinality of sync IOF is less than the cardinality of just IOF. There's so much less that you can do with sync IO, and then it makes it so you can't predict. You can predict more about it. In fact, if you can get away with having your own even smaller predicate, then go for it. Generics also really really shrink the cardinality of your code base. And beyond just finding generics for generics' sake, at another level, to keep shrinking it even further, you can try to find algebras or things that hold universally. And you can see that in this particular example, when you have to, it was for the validating example in the blog post, when you need to get when you've already decomposed something into a sum, and then you go from the first element to the true or false, right? Is it valid or not? And then the second element, is it valid or not? You can maybe reuse a function that makes A and B generic, and that'll give you 256 possible functions that you could do. But you could always return, ignore the inputs and return false, or you could run one function and return it or return the negation, so on and so forth. Or you find a law that holds, an algebra, and say, well, wait a minute, I can also, Boolean is common in all three points, and actually, if I make that generic as well, then there's only one function that fits. There's only one function that will actually fit this type declaration. And yes, the catamorphism for sums is unique. So you've gone down, just with this example, just by making the end result generic as well, you go down from 256 to 1. So briefly, start with your domain types. And this is where the real shrinking happens. This is where you get the most bang for buck. Then you can look at what things you should be able to make generic, where you're asking, where you have too much information available in the functions you've written, and pull stuff out. And then you could try to find common algebras or reuse common algebras. That's why CATS is such a valuable library to learn. Don't get me started on traversable. Everything's a traverse, right? We went through common ideas from the OOP world, right? Principle of least astonishment. That's maybe the inspiration for why, catamorphism is either's fold. Sorry. The whole thing starts off from this least astonishment, but it just connects again with like single responsibility from the sum example in the first slide, and the YAGNI. This one is super curious, because we will make the mistake, I'm going to call it a mistake, to use the more general parameter as an input, right? You might say, hey, I want to calculate the perimeter. Currently, I'm thinking of a square, but maybe I'll need rectangles later. No, don't do it. You're just going to grow your cardinality needlessly. You're going to maybe have to check that that the for nulls in the width and the height, or check that they're both not negative, instead of just knowing the side and multiplying it by 4. So it connects to property-based testing by the simple idea that, well, you will actually get better results. It'll make your property-based tests faster. It'll sample a much larger fraction of your model. So super nice. And then optics, I'm not going to go sort of show why, but optics gives you extra tricks on how to shrink the code base. Think about having a simpler method that works on, I don't know, some smaller type. And then you have a lens from a larger type to that method. You can reuse, you generate in your code simply put it, let's say the mirrored version for the larger cardinality without actually ever having to add it to your code base. So it starts to defend the use of optics in multiple places. And same idea for recursion schemes. You write a quick algebra and you avoid infinities by removing the recursive bits of it, and you keep surprises of your code base to a minimum. And also, it makes it more provable, etc., etc., etc. Here are some references.